Good morning, everyone. My name is David Alberto Nevarez-Saenz. Today I'll be talking about additive manufacturing of architect ceramic foams for noise reduction. This work is possible through the work of the aerospace department and the mechanical engineering department and the School of Art, Design, and Creative Industries here all at Wichita State University. Aircraft noise pollution is a big issue in cities where there may be airports around. It's been directly related to some health issues that some researchers have looked into, which include cardiovascular disease and sleep disturbances. This problem is bound to increase because of the improvement of different technologies, including the electric vertical takeoff and landing and other electric aircraft that will be more available in larger cities. Now, most of the noise comes from the engines on the aircraft, and there are some solutions to minimize the sound. Two of the solutions include the honeycomb sound absorbing liners and fiberglass blankets. The problem with the honeycomb sound absorber is that they're usually located in the low pressure compressor and by the combustion chamber of the engine. They work in those parts, but we would like to look into more technologies that can withstand higher temperatures around 1,800 degrees Fahrenheit, and that will be located about the turbine and the nozzle. And now with the fiberglass blankets, they're usually located at the fan or the inlet of the engine, and that can directly minimize the efficiency of the aircraft. Our proposed solution is to look and study robo-casting of ceramics or 3D printing. And with 3D printing, we have the flexibility of printing different geometries. 3D printing by itself is now an affordable technology in various institutions around the country. With 3D printing, we can also use different materials which allow it to be very compatible. And lastly, we can 3D print small or large parts and mass manufacture when we 3D print. Now we are looking into ceramics because of the reason that I said. We want materials that are able to withstand high temperatures and high pressures, and that's what ceramics can do. Right now, there are other forms of 3D printing like SL. SL basically works by a laser hitting a body of resin, and that resin solidifies whenever the laser gets in contact with it. As you can see here on the screen, there's two examples. One, which has a Serafab 7500 and the Bison 1000. These two samples are of very good quality, but there's a very high price in each of these printers. Also, there's a limitation in the print volume. We're not able to print something bigger. These are small samples. Now, other applications of current robocasting include just in the art department. And NASA, about last year, they started the simulated Mars surface habitat, and WASP has 3D printed houses all across the globe. Our clear objective of our research is to develop an inexpensive novel method for 3D printing ceramic spore structures for broadband noise reduction using a modified extrusion 3D printer. For our methods, they usually start by modeling a cylinder in OpenSCAD. The reason why we're looking into cylinders is because in our acoustic test setup, that's what the test sample holder allows us to do. So in this study, we're looking at cylinders. After doing that modeling in OpenSCAD, we slice it in Cura and export the files into our Delta Wasp 2040 clay 3D printer. After that is done, we prepare the clay. Right now we are using the Wasp porcelain clay, and that is just provided by the manufacturer, and we just mix it with some water. Then we 3D print the model, and then we have to fire it to convert it from a clay to a ceramic. Some printer specifications is that this is a pressurized air system 3D printer. And what it does, there's a clay tank in the bottom here in the picture that just moves the clay down through of some hoses, and then the clay travels through the hose onto extruder system. In the extruder system, there's a motor and an auger that drives down the clay all the way down to the tip. Now, this 3D printer is more affordable than the other 3D printers that I showed you, with a price of about $3,400, and the material of the clay, it's about less than $1 per kilogram. Also, this 3D printer has a larger printing volume, which again allows us to mass manufacture or print big samples or smaller samples for our applications. There was a limitation with the 3D printer, which include that it had a 1 millimeter nozzle limit because it was initially designed for potters and artists. Because of that, we had to make some modifications. On the left, you see how the nozzle system was provided to us by the manufacturer, and then after, we had to 3D print an auger, and we had to get a nozzle tip from our local bake store. After our modifications, we could see that before and after, there was some big differences. Before, we had a limitation of 1 millimeter, and then after, we were able to print all the way to 0.4 millimeters. Some of the initial prints to get familiarized with the printer is just simple geometries. As you can see on the top left, we looked at what it was made for, which is for potters and artists. We just wanted to see how we could modify the clay, what it could do at the time. And then after, we made some adjustments and saw that it could 3D print smaller nozzles and sizes. Now for this study, we looked into relative densities between 25 to 40%. And the relative density just tells us that 25% it's solid, and the other 75% is hollow in our samples. With that, we had to look into the as printed and as fired to make sure what we model is what we actually want. So we looked at some of our measurements under the microscope. So this was designed to 3D print 0.4 millimeters, as you can see the line thickness, and that before firing it, it was about 0.48. And then after firing it, it shrunk and got to 0.43. So what we had to do is we had to look at the shrinkage when we designed it, when we printed, whenever we let the sample dry, and then whenever we fired it. That way, we could scale accordingly. And what we found is that to get the measurements that we want for our acoustic test setup, we had to scale our samples by 120% in the XY direction and 124% in the Z direction. Now, after doing that, we looked at our acoustic data and for the different relative densities. So if we look at the 25% relative density, we have a peak in our frequency at about 3,500 with an absorption coefficient a little over 0.6. What the absorption coefficient tells us is how much of the sound it was absorbed by the sample. And now a similar trend happens between 25 to about 32.5% relative density, and by the peak going to lower frequencies and having a higher absorption coefficient. But in higher relative densities, that is not followed through the samples. We believe that may be because of the quality of the 3D printed samples. Now, our next steps are to look into different geometries that we can print. In the pictures shown, all we did was just basic line infill. So it would be interesting to explore others, gyroids or other geometries. Now, this clay was provided by the manufacturer. In the future, we hope to create our own clay. We already started with creating our own clay, but we would like to add more and explore a little bit more before we move forward with that. Now, this summer, we're looking if we can connect the arts with the engineering, and we are collaborating with the art department in doing that. Relating to our creating our own clay, we will look at maybe creating carbon fibers in our clay and testing the strength and the heat resistance of our samples. And now this summer, we also ordered a new Stoneflower 2.0 multi-material printer, which allows us to have more than two clays with two nozzles. So we will look into further research in that aspect. Now, here are some of my sources that I mentioned throughout the conversation. And thank you for your time. If there's any questions, I'm open to all. Thank you. Noise pollution is basically if you're out by your home at a public area and you hear an airplane or a helicopter, that's noise pollution by itself. We have hundreds, if not thousands, of flights each day here across the US. And if you just hear one aircraft by itself, it's loud. Imagine hearing those aircrafts every single day. And especially if you live close to an airport, it can be quite annoying. And it's just simply that if you hear an aircraft, that's part of the noise pollution. Thank you for your question. With 3D printing, what one usually has to do, and what we did for our study, is just we go to a software on our computer and we designed just a geometry, whatever we want. 3D printing is very flexible, but for our study, all we did was we designed a cylinder, and then in that cylinder, it had different lines in between, and the lines would like zigzag between each other like so. And what we had to do is each line has a certain thickness and it's at a certain distance away from the following line. So what you do is you model that in your software on your computer. After that, you send your file to a slicer software. And in the slicing software, what you are able to do is you are able to tell the 3D printer what you want. So you can change the speed in which the 3D printer prints. You can tell the layer height, the thickness, and you can do very different parameters that you have the flexibility to do. And in our 3D printer, we focused a lot on the extrusion rate, which is the amount of clay that comes out. And we looked at the pressure. So if the pressure is higher in our 3D printer, more clay wants to leave the 3D printer. So we had to find a balance between high pressure, low pressure, and there is that. After you have sliced your model, what you do is you convert that file into a G code. The G code just translates everything that you told the slicer software to do, and then the 3D printer is able to understand it. It's like a different language. It's like a G code. You tell it how much to move, where to move, and every single parameter you told it to do.